It's my pleasure to introduce Peter Molnar today from CU Boulder. Peter got his start at Oberlin College. He had an undergraduate degree in physics and then went on to Columbia to study geophysics and then on to Scripps for a postdoc, after which he joined the faculty at MIT. And if you read his blurb that he posted on the center website, after 12 years he resigned his faculty position to return to a life of a postdoc, meaning pursuing his research interests full-time. And then eventually that led him also to move to CU Boulder and join the faculty there, where he still is today. Peter has a long, distinguished career and many accolades and many achievements. One of the big lifetime achievements came in 2014 when he was awarded the Crawford Prize by the Royal Society in Sweden, which is often considered by most to be the Nobel Prize of the earth scientists. And that just is testament by his friends and colleagues who nominated him for that award, what they think of his achievements. Peter's move to Boulder, I think, also brought him closer to something that is near and dear to his heart, which is high terrain. And that's one of his common themes through all of his work, is to try to understand the origin of high topography on Earth, how it relates to continental plate tectonics, to geodynamics, and what he's going to talk to us today about how that topography influences the Earth's climate. Thank you.
So, thanks, Marin. As I told some of you, I don't like to go to scientific meetings because I don't like 5-minute conversations that get interrupted. I like 30-minute conversations where I can engage with people, and I've had a great day today. I've had a whole series of them. It's been wonderful. I also am of the feeling that the essence of a good life is to meet challenges when they come, and I'm delighted to take on this challenge. This is a new challenge for me, to give a talk like this to, in large part, a non-scientific audience. So I appreciate this invitation. I hope in an hour I'll still appreciate it, but we'll see. So, monsoons. We all have an image of a monsoon. This is a photograph I lifted from the web of very, very heavy rains. But I'd like to give you another view. You know this old cartoon of blind people looking at an elephant. An elephant is a big snake. Actually, it's a tree stump. What does it say here? What we're saying is it's like a sheath of leather, or it's a furry mouse. And I want to leave you with the impression that the definition of a monsoon is in some ways elusive. Let's just start with where the word comes from, monsoon. The English word monsoon has its origin in the Arabic word mosim. I think it came via Portuguese, the word moçal, but anyhow, it means season. It has nothing to do with rain. The origin of the word is with seasons. And the logic behind that has to do with the winds. So this is 4 maps of winds in the Indian Ocean. Here's India lying up here, coast of Africa, Madagascar, February, May, August, and November. Now the monsoon, as we know it, is strongest in August. The colors are showing you wind strengths. It's hard to see the arrows, but the arrows are blowing along the coast of Africa and then across India here and into the Bay of Bengal at this time of year. In the winter, November or February, the winds actually blow the opposite direction. This is the origin of the season part of this. And so this comes from Arabs trading along the coast. Here's India again, the coast of Arabia. In winter, the Arab traders would sail along the coast of India down to Africa, where they would, they sought, we won't talk about what they were after in most cases, but anyhow, they picked up individuals, we'll call them. And then come summer, the winds would blow the other way and they'd go back. So the origin of the word monsoon comes from the seasonal winds that the Arab traders used long before, probably long before the Europeans got there. Now, in addition, the sea surface temperatures vary. So this is, I don't know why these are months that are what they are, but we have December, August, May, and November. These are nearly the same. But in August, when, right, December and November, they're almost the same. In August, when the winds are strong winds blowing along the coast, in fact, blow the surface water off to the southeast, so cold water upwells underneath, and you have cold water along the coast of India. the coast of Arabia and the coast of Africa in here. The winds blow the other direction, as I said. You don't see this big effect oceanographically that you do see in the summer. Well, the topography is very important for the rainfall and for the monsoon itself. Map of Asia, the high Tibetan Plateau, the winds in summer, this is June, July, and August. Winds coming up the Arabian Sea across India into the Bay of Bengal. If one looks at the rainfall, you think monsoon rainfall over India. In fact, most of the rain isn't over India. It's hard to see India. India lies down in here. Here's the island of Sri Lanka in here. The edge of the Himalaya lie across in here. Big rains along the west coast. This is an orographic effect. The winds are blowing towards the coast. Suddenly you have a wall of mountains, 2,000 meters high in places. You dump a load of rain out in here. And much of the rain along the coast over here, where again you don't have big mountains, nothing like the Himalaya, but a lot of rain over here. Across India, actually there's not all that much rainfall, right? We think of India as being the monsoon where rain is heavy, but it's quite variable across India, and it's not anywhere near as big as in other places. Another way of looking at this is a series of seasonal rainfall in various places. In each of these plots, the left is January, the right is December, so you have big summer peak in monsoon rainfall, hence the monsoon. The horizontal lines correspond to 50 or 100 millimeters per day. So over here on the west coast, you get this big peak in rainfall that I mentioned before, getting more than 100 millimeters per day during the monsoon season. And you can see these are different wherever you go. You go out into the deserts out in here, you don't have much rainfall. You go way up in Pakistan, you actually have 2 seasons. Let me call your attention to this place down in the south east coast of India, and you actually get your maximum rainfall here in winter. You may remember last year, huge floods in Chennai, a big city down over here. We wouldn't call that monsoon if we thought about summer rainfall. Some would say, well, that's winter monsoon rainfall. The winds, again, are blowing the opposite way from the Bay of Bengal in towards the southwest, and you get orographic precipitation on that side, this big peak, completely different. So if we go back to the elephant, a monsoon is heavy rain in summer. If you're in Chennai, a monsoon is heavy rain in winter, or it could be cold water if you're off the coast of Africa, but it's strong winds for sure if you're an Arab trader working along the coast. Monsoons are quite different depending upon your point of view. Now, one last little fact about the monsoons, they vary, but they don't vary by very much. This is a plot of anomalous rainfall during summer. This should be summer, so this would be June, July, August, and maybe a bit of September. So the 0 is the average. That's the typical monsoon. These low bars, this is getting to be 30% lower than normal. This is the worst monsoon in history. Tens of millions of people starved at this time back in 1877 or 78 during the worst of all monsoons. But the fact I want to leave you with is the average monsoon varies by only 10% from normal. Or another way of saying this, one standard deviation is 10% different in rainfall. This is a weak monsoon, this is a strong monsoon, and it's just 10% of the rainfall. If you think about it, if you lost 10% of your salary, you'd probably still be okay. You wouldn't like it. If you got 10% more, you'd be happy, but it wouldn't mean that you'd go take a 1-month extended vacation to Bali, for instance. 10% is not a big number, but it's a huge number in India. 10% less rain, and it's a disaster for much of India. It's a small amount. So let me leave you with an interim summary. I'm going to change directions next. The monsoon means much more than rainfall. It comes from this word mosim, which is rooted in the word season. I don't know that season is a literal translation of this word, but it's a very strong connotation associated with trading and with winds, not rainfall. Rainfall is far from uniform over India, and only a small difference in rainfall, 10%, can make the difference between a strong or a weak monsoon. Now, I come at this from the point of view of how have the Himalaya and Tibet influenced the monsoon, and I told you this was a challenge. One of the reasons this talk is a challenge is this is a moving target. If I'd given this talk 5 years ago, I would have said something very different from what I'm going to say now, and I would have been completely wrong. So I'm a little bit at risk 5 years from now. Well, be careful what you believe, I guess is what I should say. Okay, so Himalaya and Tibet. To discuss how they relate to the Indian monsoon, we have to understand how these have grown, how the how the Himalayan and Tibetan Plateau have been built, and how they've evolved. Well, one thing we know how to do is calculate where pieces of continent lay at different times in the past. So this is the Indian continent. This red is Tibet in here. And these symbols show you calculated positions of where the northwest corner of India, the northeast corner of India lay at different times in the past, going back to almost 70 million years ago. 70 million years ago, most of India lay south of the equator. The equator comes across right through here. India met the southern edge of Asia sometime around 50 or 40 million years ago. So when India lay roughly in here. India's moved a long way north since you finally closed up the ocean in here. And if we plot the distances from their present position going back 6,000 kilometers as a function of the time in the past 10 to back 70 million years ago, India was going north fast on geologic timescales by more than 100 millimeters a year. That's more than 4 inches a year if you are SI unit challenged. And then it slows down, and we think it slows down because suddenly you lost a lot of the pull on India that was drawing it north, and it's continued to slow down since that time. We can calculate this pretty well. Now I'm going to show you more than once. I'm going to show you an animation made by Tanya Atwater of India moving towards Eurasia. This is a cross section. This is a cross section into the Earth. So here's India. An ocean lay between India and southern Asia over here. The tan is crust in the Earth. This is roughly 35 kilometers thick under India, maybe 40. It gets much thinner under the oceans in here. Then the warm color, this is all mantle. This is what we call the lithosphere, the strong part of the mantle. And so at first, just watch what happens as we move India north here, assuming I can make this work. So India goes north. It slides underneath southern Asia. It's pushing Asia further north too. And you're slicing pieces of India off the top of the Indian crust, building high peaks. So there, if you like, is Mount Everest standing up here with a bunch of slices of Indian crust. If we were to back up and look at the configuration that we had at this time, I'm just going to show you 2 cross sections, one cross section on the northern edge of India, one cross section on the southern edge of Asia here, with no vertical exaggeration. We have the crust of India with some sedimentary rock on top. This crust thins as you move into the ocean. The blue is ocean. We have sedimentary rock on the edge here. This is like the Atlantic margin today. If you were to go east of New York or east of Savannah, Georgia, you would see something similar to this out into the ocean. And then on the southern edge of Asia, we think we had a thick crust under here like the Andes back before India met. These thin crusts, this green is oceanic crust, different composition from the continents over here, just slid underneath the southern edge of Asia. Slices of this got taken off to build a little wedge out in here, filled up with some sediment. This is a typical margin. This is what you would see off the coast of South America right now. You have the Andes up in here, deep trench out in this area, and oceanic crust and upper mantle subducting underneath. Well, then you get this continental collision. The crust of India meets the crust of Asia. You start to underthrust that crust, and then what we think happened is a new fault broke through. That yellow line is showing you a new fault that broke through sometime after 45 million years ago. That thrust fault was active around 20 million years ago. India sliding underneath southern Asia, and underneath this stack of rock in here, plunging down there, and a new fault broke through. And again, present day, we have another fault down in here, stacking up crust. So the Himalaya consists of a bunch of slices of India's old crust. A simple cross section, this is the edge of Asia as it existed before India got there. This green, that's a remnant of the old oceanic crust. And then all the rest of this is Indian crust, sedimentary rock deposited on the edge of India before the collision, back when you had an Atlantic-type margin. A big thrust fault in here, which has been subsequently warped by slip on another thrust fault in here. But all this is stacks of crust of India, just piled on top, one on top of another. It's as if you took a deck of cards and tried to slide it underneath the doorway. The doorway was a little low, and you just stacked all those cards back up on top of what you were pushing underneath. you have it's a bit more complicated. You have some granite in here where you've melted the crust. Okay, now let's go back to Tanya's movie. Now watch this side of it over here. Don't pay much attention to what's happening in the mantle. I'm not going to pay much attention to that myself today. It's where I've spent years doing my research. That's not quite true. I've never been there, but I have studied it for a long time. So now we move India further north, and what happens is you shorten up Asia's crust in here with faults and folds, which you don't see, and you make a big, thick crust. This is the Tibetan Plateau in here. It's made of thickened Southern Asian crust. So I'm going to give you now a quick summary of the timing of all this. India collided with Southern Asia, hence Southern Tibet, sometime around 45 or 50 million years ago. Before that, you had oceanic crust. You had a big, wide ocean in between. Those of you who know, it's probably a little more complicated than this, but let's not worry about that now. India's penetration into Asia has built and continues to build the Himalaya. The big earthquake in Nepal last year occurred essentially along this segment right in here of this thrust fault where India is sliding beneath the Himalaya. Slip on a fault in here of a few meters is what gave rise, or what happened during that earthquake. India's penetration into Asia has also foreshortened and thickened Southern Eurasia, or Southern Tibet's crust to build the Tibetan Plateau. These are all qualitative statements, or mostly qualitative statements, so one's pretty safe with those. But now one can ask the question, what's happening now? And it's changed. I want to digress briefly with a little bit of terminology that we use. Types of faulting. I've probably already used that word. I hope I haven't confused anybody. We have three kinds and mixtures of them: a thrust fault, a normal fault, and a strike-slip fault. A thrust fault is when the crust is shortened horizontally. That's what these arrows show. And one piece of crust is thrust on top of another piece of crust. So in this case, the Earth's crust contracts and thickens. Normal fault is the opposite. You pull blocks of crust apart. The one on top slides down relative to the one underneath. So the crust extends and it thins. And then the strike-slip fault, one piece just slides past another. Well, the Earth's crust thrust faulting is what builds mountains and high plateaus like the Himalaya and the Tibetan Plateau. Crustal shortening, thickening of the crust. Different in the Himalaya, where you have these very gently dipping faults and you've stacked up layers and layers, whereas within Tibet, it's more distributed and maybe at somewhat different times. By contrast, normal faulting destroys mountains and plateaus. You're pulling everything apart. And you can imagine you put a pile of paper on your desk. Many of you are academics, you know what it's like to have a pile of paper on a desk. And you know, if something happens and the papers all slide off onto the floor, the level comes down. Well, think of these as sheets of paper. They slide apart and the level comes down. Well, what's happening in Tibet today? Normal faulting. This is a picture in northern Tibet. This is relatively young rock that used to lie atop rock over here. It's come down, and these arrows are showing the sense of motion. This is Peter Yakovlev, Michigan student a few years ago, working in this area. This is costly. The cheap way to do all this is to study earthquakes. So I'm going to try to take you through this. Each of these symbols shows the location of an earthquake that we've studied. When an earthquake occurs, faulting, slip on a fault occurs, and we have three types of faulting. The black ones in here show strike-slip faulting, one block sliding past another. The blue ones are showing you normal faulting within Tibet. Normal faulting is prevalent throughout the high part of the plateau. This is what's happening today, all across Tibet. That photograph I showed you of Peter Yakovlev is way up in here someplace. We still have thrust faulting, but only on the margins. Around the Himalaya, we have thrust faulting. We had thrust faulting in Nepal just last year. And around the northern margin, we also have thrust faulting. So the plateau is extending where it's high, but you have contraction on the margins where pieces of crust are being thrust on top of the surrounding regions. And if you plot these as a function of elevation here, the normal faulting, all but one exception, this guy, which is different, and I can explain it, no problem. The high ones are all normal faulting, And then the thrust faults are lower, and you might say, well, what's wrong with that one? Well, that one's this one up here, and if the earthquake is mislocated by 20 kilometers, and actually we're 20 kilometers to the north, it would move way down here without any problem. So this division between normal faulting up high and thrust faulting down low is quite prominent. And I should point out that normal faulting cannot build a plateau. Remember, that's the papers falling off the floor. If you want to pile up papers on your desk, you push them together. You don't let them pull apart. So we have to have had some kind of change in what's going on because we built the plateau by thickening the crust, and now it's falling apart. And we can ask when did it change? It's changed, right? We started building the plateau a long time ago. Well, this is a compilation of various studies. They're virtually all, not quite all, I think, but virtually all 21st century studies of different normal faults. And the ages here, 9 million years ago is what this means. This one, the Takolograben, many of you may have walked up to Annapurna and Dhaulagiri, and here that's where the Takolograben is. 11 to 9 million years ago, and you make your way around. Most of these are somewhere in the range of 10 to 15 million years old. So we infer from this, though I look forward to more data, the onset of rapid east-west extension of the plateau and crustal thinning began sometime around 15 to 20 million years ago. Now, we know that this extension is taking place today. In fact, with GPS, we can measure how rapidly that's taking place. And we can then use that to estimate how fast the crust is thinning, because if you're spreading this apart, the crust is thinning. If we know that, we can calculate how fast the surface is going down, and then we can extrapolate that. If we extrapolate present-day strain rates back to 10 or 15 million years ago, this predicts a drop of 1,000 meters in the mean elevation of Tibet. In other words, if we as humans had evolved 10 million years earlier than we did, boy, would we have ski areas. This would be 6,000 meters high, not 5,000 meters high. This would be a lot colder than it is, and a lot harder to work, I might point out. Politics might be different too. Anyway, the point is that it appears that Tibet used to be much higher. 1,000 meters, that's a lot, much higher than it is today. And one last picture of this kind. This is a compilation, you can't possibly digest all of this, but a compilation of studies that have been made surrounding the Tibetan Plateau, all around the edges, one in the middle, a particularly good one. These are showing when deformation within the Tian Shan up in here accelerated, 13 to 11, 11 to 10, 7 million years ago. The Gobi Altai, 5 million years ago. When Lake Baikal opened up, 10 to 7 million years ago. All around the edges, big deformation, folding up of the Indian Ocean floor to the south, roughly 8 million years ago. All around, you have these numbers again in this 10 to 15 million year age range. And this study was a particularly good one. It was done, Alison Duvall was a student here working with Maroon, where they, it's too long to describe what they did, but the conclusion is that this whole area tilted so that it could drain more rapidly sometime in the range of 4 to 11 million years ago. So I want to leave you with this image of what Tibet, the way to think of it, particularly if you're not a scientist. Tibet is a humongous piece of camembert cheese spreading out onto China and the Indian plate. There it is up here. And if you're a yuppie from the 70s, maybe you prefer brie, but I prefer camembert myself. This is the way to look at it. It's a big, high region, and it's spreading out. So the thrust faulting over the Himalaya is due to spreading over India. The thrust faulting within the Himalayas, spreading out there, spreading to the northeast, and the surface is coming down. So to just give you a quick summary, India collided near 50 million years ago. The Himalayas started to grow around 50 million years ago when India collided in here. I could run this one more time, I suppose. India collides, notice 50 million years that just went by. That's when you're colliding in here. We can move on. Southern Tibet was quite high before the collision occurred. We're pretty confident of that. So this area was high even before India got there. But a big change occurred somewhere around 15 to 10 million years ago. The thickening of crust either stopped here or, in fact, probably stopped before then, and the surface began to subside. When the surface of Tibet began to spread apart. So, in a sense, Tibet began to collapse. The camembert cheese got ripe and it spread out onto the Indian plate. And then Tibet's height might have been 6,000 meters back at this time, 15 to 10 million years ago. Okay, let's now switch back to the monsoon. The standard view for decades has been that heating over Tibet has heated the air, and that air has risen. So look at this as a profile where the equator is down here, the Indian subcontinent would be here, Tibetan Plateau, and here obviously vertically exaggerated. 35 north, that's the northern, that's well into Tibet. So this area is high. The air on the surface of Tibet is much warmer than it is at the same elevation out in the free atmosphere. So this is warm compared to the surrounding air. It rises. You can't just create a vacuum in here. This draws air in from the Indian Ocean. That winds blowing across here evaporate seawater, so you bring moist air in here. When the moist air condenses, it gives up heat, you rain out, and with latent heating, you heat the air even further, so you get further ascent of the air, and then the cross-equatorial circulation. And Tibet is fundamental in this picture. This picture is actually one I drew, but it wasn't. It was what we all believed back a long time ago. I just put it in here because if I'm going to say somebody's wrong, it's best that I admit that I'm the one. Anyhow, you would expect a hot upper troposphere over India and cooler, though not cold, upper troposphere over here. Troposphere is the part of the atmosphere below the stratosphere. Temperature decreases up through it. Well, we started getting hints that there was a problem. Bill Boose's name is going to come up a few times. This is the July temperature, 250 hectopascals. This is roughly 13, 14 kilometers high in this area. And the warmest area, it's sizzling up there, 240 kelvins, or if you like, minus 33 degrees Celsius. That's about minus, 25 degrees Fahrenheit, is not centered over Tibet. It's centered to the south. The heating doesn't look like it's coming from Tibet. It's coming more from northern India, the hot atmosphere in here. Okay, I've got to introduce a concept here to make the rest of this clear. I hope no one's intimidated by a formula. Moist static energy. This is the quantity that we should be thinking about. And it's not energy quite, it's energy per unit mass, those of you who remember your high school physics. We give a symbol H. This includes the effect of temperature, so this is the internal energy. Cp is the heat capacity constant pressure. So if you have warm air, that contributes a positive or a larger term than if it's cold. LV, latent heat of vaporization. Q is the concentration of water vapor in the atmosphere. So if you have moist air, this term is big. If you have dry air, this term is small. And then this is potential energy, GZ. And this increases as you go up. And you know this. When you climb the stairs, you have to do work. It takes a lot of energy to climb stairs because you're increasing Z. You jump out the window, and you lose all of that, and you pay the price. But it doesn't take any energy for you to jump out the window. You just let gravity do the work for you. This quantity is conserved, essentially conserved in the atmosphere. So that if you go up in height, let's just look at that in a cartoon, this is conserved. So if the air rises, you gain potential energy. Well, if you're keeping that constant, you've got to lose something. Well, you all know it gets cooler as you go up. Temperature drops as you go up. Increase Z, decrease temperature. But eventually, the moisture in the atmosphere reaches a point where the atmosphere is saturated. You lose that moisture, it rains out. You lose it as precipitation, so Q drops. And what that means is that as you go higher and higher, the temperature doesn't decrease quite as rapidly as it did because you've lost some of that energy with the Q. And this is part of why you get a rain shadow. The air rises up over a mountain, loses its rainfall, loses its moisture here, goes up over the top, comes back down. When it comes back down, it warms again. Z decreases as you come down on this side, but it's warmer on this side. Nevada's warmer in summer, especially, over here at the same elevation on the western side of the Sierra Nevada, for example, because moist static energy is conserved. This is a wonderful quantity that we use because it's conserved. Now, think about India in June. If you've ever been there, in June, you probably thought to yourself, that's not something you ever want to do again. Because it's very hot, it's got a big T, and it's very humid. It's got a big Q. It means the moist static energy is big in India. Both of these are contributing, and it turns out probably the more important one is that. Anyhow, in terms of how you feel when you're in India, that's much more debilitating, in my experience, than the temperature. You got to change your clothes a couple times a day because you're sweating all the time. So what does theory predict? The theory says that you should have ascent of air where you have a maximum in the moist static energy. This is the maximum here. And you'll have ascent in this area, and then that ascending air will diverge. Some will go north, or some will go poleward, and some will cross and go equatorward. And the maximum rainfall will be just slightly to the south of this. There's a simple explanation because there's more moisture on this side than there is on this. You'd expect this to be slightly equatorward. The maximum ascent rate is slightly equatorward also of your maximum moist static energy in here. So this is, it's in a sense, it's almost common sense where you've got the most moist static energy at the surface, both because the air is hot, which makes it light, and because it's moist, which also makes it buoyant. Moist air is less dense than dry air. That air is going to rise. It'll go to the top, make it hot up here, and then that air will diverge. And while it's doing that, you'll get all this rainfall. And if you look at data across India in this case, so the equator is here. You're looking from the southern hemisphere all the way north. Rainfall is in blue. The peak in the rainfall lies here, around 20 degrees north. The peak in the moist static energy is slightly poleward, as it should be, as theory predicts. If you were to look at the temperature alone, take the moist static energy without moisture, so you would be ignoring the moisture, the peak actually would lie farther north. The moisture is really crucial for determining where the peak in the moist static energy is. And if you look at this now, this is July, the maximum moist static energy is not over Tibet. So here we have the coast of India, Sri Lanka down here. This is Tibet crudely outlined. It's actually outlined in pressure space, not elevation space. This would be the Zagros in Iran. Down here, the high plateau of Ethiopia and Kenya. But the Himalaya lie in here. And the maximum in the moist static energy, not over Tibet, but over northern India. So Tibet doesn't look like it's particularly crucial. Now this next slide is my most challenging slide, and it will take me a little bit of time. 9 plots, 3 of them, this is temperature in the upper part of the troposphere, 175 to 450 millibars. This is in the range of roughly 5 kilometers to, let's say, 13 or 14 kilometers elevation. And red means it's warm. So 3 cases. Subcloud moist static energy. This is the moist static energy down near the surface. Again, red means big numbers. And then precipitation and winds. Red means heavy precipitation. These are all numerical calculations by Busin Kwong using a general circulation of the atmosphere. The top one is present-day topography, what we would have today. So here's India down in here. Here's the Tibetan Plateau up here, coast of Arabia coming down further south, going over Indonesia and Australia. The middle one, the topography is gone. You basically take a rolling pin, go out and squash all the topography, get rid of all the topography. So there's no mountains, no plateaus, no mountains, nothing in this case. And this third one down here is without a Tibetan Plateau, without all this high terrain, but still with the Himalaya and actually a bit of the Hindu Kush coming over here. So this is a narrow mountain range. It's the southern edge of Tibet, if you like, but without the Tibetan Plateau itself. So let's look at the temperature in the upper troposphere. It's high over India when you have a Tibetan Plateau and the Himalaya. It's high over India again when you have a Himalaya, but no Tibetan Plateau. But it's not. It's the locus of the warmest air is actually quite a bit farther south. Notice this is the northern edge of the Bay of Bengal here. This maximum in upper atmospheric temperature, which is not as warm as in these 2 cases, this maximum actually lies way down here in the Bay of Bengal. It's shifted southward. So not only do the mountains give you a hotter upper troposphere, they give you the hottest upper troposphere is farther north than where it is without the mountains. But it doesn't matter whether you have a plateau. It matters a little bit. So either that red blob in there is over Tibet and you don't have that red blob. But the big picture, Tibet doesn't really matter. Subcloud moist static energy. Remember, theory says this is the key quantity. Again, it reaches a maximum over India. There's a little maximum over Tibet, but the big maximum is over northern India here. Again, without a Tibetan Plateau, again, the big maximum is over northern India. If you take away the topography, the maximum is much further south. It's over the Bay of Bengal. And a big, a gradual gradient going from air with low moist static energy up here to increasing as you come further south. And finally, the rainfall. The rainfall is the same, pretty much the same, whether you have Tibet or you don't have Tibet, as long as you have a Himalaya. This is quite independent of the Tibetan Plateau itself. But if you take all the topography away, you just don't get any of that rainfall at all. So what's going on? Busen Kwang's thesis, which I subscribe to completely, is that the key is not Tibet, it's not heating over Tibet, it's that Tibet is a barrier. Tibet is a barrier to the circulation of low-level air. You have air with low moist static energy in the north. It's cold and it's dry. If you have no barrier, that air can then penetrate southward into India. You get this big gradient. It can push the locus of the warmest and most humid air southward, and it also dilutes it, so it prevents this air from being as moist and as hot as it would be if you didn't have this barrier. It's the barrier that's important, not the high plateau. So, if we ask the question, how does the Tibetan Plateau affect the Asian monsoon? Tibet blocks the flow of cold, dry air, cold and dry. Cold means low temperature. Dry means low specific humidity, low concentration of water vapor, hence low moist static energy. It prevents that air from mixing with the hot, moist air over India. Here's the source. If you dilute this hot, moist air with all of this, you're going to weaken the monsoon. That's their thesis. So is Tibet important? Is it even necessary? Well, I'm going to pursue this in a couple of ways, in part because, as you'll see, I've spent so much time, I can't just let it drop. But how might we look at this? What's a test? And a test of whether the heating over Tibet matters would be to correlate moist static energy over Tibet. Moist static energy is the key quantity, right? It's whether the air is hot and it's moist. Correlate moist static energy over Tibet with monsoon rainfall over India. We're now using the definition of the monsoon with rainfall. So we're going to correlate this quantity over Tibet. And the logic, of course, is that this quantity will be large over Tibet, not just because of that, but because you'll have moisture, and this will be warmer air here than warmer out there. So we're correlating that with rainfall over India. And this is broken into plots for 3 times. This is the early monsoon season. We've correlated May moist static energy with May 20th to June 15th rainfall. This is the early season. Red means positive correlation. The correlations aren't great, but 0.4 to 0.6. This is definitely statistically significant. This says that in the early monsoon season, heating over Tibet does matter. This is the late monsoon season. Correlating in September moist static energy correlated with late September, early October rainfall, and again, a big, not big, but a positive correlation. This is what you get in the main monsoon season. Very weak correlations. Really nothing much at all. I would use the word zilch to describe this. A way to think of this is you've all taken your children to daycare in the morning. If you get there early, it's calm, you can talk to your child, you can engage the child, you can have a good conversation, you can talk to the teacher and the child, everything is fine. If you're the last parent in the afternoon to pick up your child, you can talk to your child, engage the teacher, there's no problem. But if you arrive when school's in session, it's hopeless. You can't talk because it's chaos going on. What we think is happening is, yes, Tibet matters in the early season, it matters in the late season, but when the monsoon is in full swing, Tibet's really not very important. Many other factors, which I don't know, are playing a role in deciding whether Tibet is important or not. Okay, so the effect of the growth of the Tibetan Plateau on the Indian monsoon, maybe there's none. That's kind of the argument building on what Bill Boos has said, that all you need is a Himalaya, you don't need a Tibet. The southern edge of the Tibetan Plateau is all that matters. Or maybe there's an influence in the early and the late seasons, but not when most rainfall falls. So Tibet is not very important. Well, I've been at this for 25 years, and it was great for a while. thought I was right. I've been trying to learn enough atmospheric science to show how Tibet might have affected the monsoon. And I keep trying. So I'm now going to take you on one last desperation attempt to show how maybe Tibet, a part of Tibet, has affected things. So I go back to a figure that is similar to what I was showing before. All of these are studies that have been made by various authors, and from which they've inferred that there's been outward growth of Tibet or surrounding regions. So this would be the Chilian Shan surrounding Tibet coming out in here. You may recognize some names in here, down here. This, as I pointed out, this is a beautiful piece of work by Alison Duvall and her advisors, where Tibet seems to have been tilted, and in this case, let's say Tibet rose and you tilted down, so you could erode faster over on the eastern edge of Tibet. So all of these are meant to suggest that the eastern edge of Tibet has grown in the last roughly 10 or 15 million years. On this side are a couple of time series that are meant to suggest maybe that the monsoon has gotten stronger, but how, we're not sure. Each of these two, and this one down here, the present day is on the right. The red lines are 5, 10, 15, in this case 20 million years ago. These are isotopes found in carbonate sediments. This one from Carina Horn is the fraction of Germinii. Germinii is grass. So this is suggesting that sometime between 5 and 10 million years ago, there's much more grass growing in this area. Forests gave way to grass. The best evidence for the case I want to make is actually from Pakistan up in this region, where there's been a transition from forest-dwelling animals to grass-dwelling animals. So you went from browsers, the ones that ate in the trees, giraffes, for instance. Giraffes maybe not with necks as long as the modern-day African giraffe, but animals that ate leaves, and then sometime between 5 and 11 million years, they started eating grass. Forests went away. That suggests it became more arid to get you to grasslands. Well, if we go back to, what did I do? Oh my God, oh no. It's okay, right? I hit okay. Let me just get right down to where the slide was. Sorry, I don't know what I've done. Well, let's come here, and I'll just advance it. Try to advance it. So, again, back to Busan Kwang's work. This is a little bit hard to explain, but here's topography without a Tibetan plateau. So Tibet would lie up in here. The southern edge, the Himalaya, would be in here. India, this is the edge of India, Sri Lanka, coast of Arabia, coast of Africa. This is the difference in two calculations that they did. One case when there is a Himalaya, but no Tibet, and then subtracting Himalaya with Tibet. So to explain this, this blue means there's more rainfall in eastern Tibet if there's a high plateau. In other words, the building of a high plateau out in this region should increase rainfall out here. And this is a region with a fair amount of rainfall. This is eastern Tibet. It's quite a wet area now. I want to correlate that with what's happening in Pakistan. So here's the coast of India, the Himalaya coming across. I'll explain this figure in a minute. But this blue box, we're looking in this blue box, when does rainfall occur there? This is the seasonal average, January going through to December over here. Most of the rainfall is in July and August in this period. So the next part of this is to look only at July and August. Who cares? There's not much rain out here. When does it rain here? Again, this requires a bit more than I want to explain, but you'll notice that it's blue here when it's red there. The way to look at this is when it's raining here, it's not raining there. When it's not raining in eastern Tibet, it is raining in Pakistan and northern India over here. So if you can increase rainfall over here, you would dry out that region out in there. And that's the argument here. Eastern Tibet has grown. Rainfall, we are predicting, increased because of that in the past 10 million years. The increase in rainfall due to then atmospheric circulation would induce an aridification of this part of the world. The forest-dwelling animals wouldn't have any trees, they wouldn't have leaves to eat. They would go away, they would evolve somehow into grass grassland-dwelling animals that would then thrive on the grasses. So if we go back to this, the effect of the Tibetan Plateau and the Indian monsoon, well, maybe none, maybe only early and late seasons, but maybe, and I'm not going to offer you any bridges to buy, but maybe outward eastward growth of Tibet induced aridification of northwest India and Pakistan so that browsing animals gave way to grazing animals. And even if that's wrong, as I said, for 20 years, I've been trying to learn enough atmospheric science to show how Tibet might have affected the monsoons. And if I've failed, it doesn't matter. I've had a lot of fun. Thank you. We should allow all of you who want to leave, but if you want to ask questions, after they've all left, I'll do it. Ted?
Peter, one of the things that used to mystify me, but I think maybe you've solved it, is that the drilling results off of the Arabian Peninsula back in the early days said, well, we didn't get any upwelling until about 8 to 10 million years ago. And so does that lead me to believe that that great high Himalayan front didn't exist until 8 to 10 million years ago?
Okay, so for the rest of you, I don't know if I have the slide.
that one's there.
I think I didn't put it in, no. What Ted describes is a big change in the organic sediment deposited off the coast of Arabia on the Owen Rise. And there is a characteristic organism, an organism characteristic of when you have cold upwelling water, Globigerinopiloides. And today, for looking at the past hundreds of years, this is the measure of monsoon strength. When you upwell cold water, as you do, as I showed right at the beginning, during strong winds of the monsoon, Globigerinopiloides just thrives. It loves it, and it's there. When those winds shut down, it goes away. So we know, as a measure of today, it's a good measure of monsoon strength. The geologic record shows that roughly 9 million years ago, Globigerinopiloides went from being a few percent of the sedimentary record to tens of percent, of order 40 or 50%. We all believed that the monsoon got strong 8 or 9 million years ago, until a couple of years ago. It turns out, too, that this carbonate material dissolves when the pressure increases, dissolves in the water column. So if you have some plankton, some Globigerinopiloides, it sinks to the bottom of the ocean. When it gets down to a certain depth, it dissolves into the water and it disappears. This means that you can deposit this in shallow water, but you can't deposit it in deep water. What we think happened is 9 million years ago, the seafloor came up, and so you weren't depositing this, you were dissolving this before 9 million years ago, and it's not a climatic signature at all. This, I can't tell you what a disappointment this was. Oh, you look the way I felt.
Yeah.
That's, this just, 25 years of trying.
There are other indications.
Wow, yeah.
Sediment accumulation.
Pretty puny stuff. They were, a few, many. That was the Rosetta Stone. That's what we all hung everything on, and it's gone. And if it's gone, then you can make anything up with all the rest of the stuff. It all fit back when it fit, but now it's it's gone. So, good question, and as I said 5 years ago, you would have gotten a different talk, a big talk. Carolyn Badgley's work wouldn't have figured it all. I would have ignored that completely. Yeah. Catherine Badgley, sorry, Carolyn. Yes.
Can I go back to the introductory part of your talk and ask an elementary question? If two plates collide, what determines who's on top and who's on the bottom? And in the case of India and Tibet, if it had been the other way around, would the gross topography have been very much different?
The answer is definitely yes. What determines... there's a long history of one of them going down. In the Andes, for instance, I have to stand near this. In the Andes, the plate under the Pacific, on the eastern edge of the Pacific, is diving down under the Andes. You can imagine to yourself, what would happen if we put a continent on top of that plate and dragged it in? Well, it would try to dive down under the Andes. This is what we have in India. Now, if the world had been different, and if 50 million years ago, this lithosphere here had been plunging under India, yes, then we would have built a high terrain over here, probably not here. We would have, this would be our, maybe not, it's different rock, so I can't stretch too much, but yes, you would have built high mountains over here. So it's what precedes the collision that determines what goes under. And in this case, we have thousands of kilometers of material that has been subducted, that is penetrated underneath the southern edge of Asia into the mantle here. And India is just a passenger. It comes along and it faces this doorway that it's got to slip underneath, and it can't get under the door, so it gets pieces of itself stripped off as it piles on top of itself.
So how high does the Himalaya have to be that barrier keeping the cold, dry air north? And therefore, at what point would we have expected the monsoon to become strong?
Good question. The short answer is, of course, I don't know. But there, as I was saying to you earlier, there's an interesting situation. The numerical models for the Indian monsoon aren't very good. And Bill Boos has looked into this, and one of the reasons they're not very good is the nature of these models is they have to smooth the topography. Yeah. They can't put a Mount Everest in. They can't come close to putting a Mount Everest in. And there's a low point in northern Afghanistan, not that low, it's 3,000 meters high. It's where the tunnel goes through if you're heading from Kabul up to Kunduz or up to the north. But it's a low point, and most of the models have to smooth through that. It's not only low, but it's also narrow in its meridional dimension. So if you smooth, it goes down. And most of the models have the problem that they leak cold, dry air in, and they don't get a very good monsoon. If that's right, then that would suggest, yeah, maybe 2,000 meters is too low, if you got it that low. But I'd be hard-pressed to defend that number. I don't know. But I have no doubt that the Himalaya has been high for tens of millions of years, 30 million years or so. What we don't know is the Hindu Kush. I've read everything I can find, trying to get information. I've been 40 years ago. I worked in Afghanistan. I don't until we have peace in the world. I don't think we're going to be able to learn the history of that part of the world and be able to answer that question. Joel, I think you have to wait for this microphone, though. Yeah.
Sorry.
You got to be patient, Joel.
Big crowd.
Patient, you
I don't know
know.
if I can take it. It's such a pressing question. You showed at least one weather station up in the upper Indus Valley that had a double wet season, and I wonder why that is, and how big an area do you think is affected by that pattern of rainfall? I mean, is it the whole Karakoram, or is it just localized?
It's not even the Karakoram. You're talking about this one. Oh, where'd it go? Yeah, this one up here.
Yeah.
You're really probably all of this is springtime rain. This is probably due to westerly winds bringing moisture in from way out here across. And this applies to a pretty small area. Notice when you get down here or you get over here, in this area, it pretty much goes away. Now the Karakoram, of course, is this region back up in here, and I don't know about that, but it doesn't get very much rainfall either. So I don't know that specific answer. But I suspect, as I said, the two peaks. One of them is monsoon. That one. One of them is probably moisture coming from a different direction, coming from the west.
For the earthquake slide, was there a significance to the orientation of the little colored balls?
Yes.
Okay.
Yes.
I hadn't seen one of those graphs before.
Yes. If you look at these, note it's white in the middle. That means you're compressing the crust vertically. It's blue on the edges. That means you're extending out that way. So this is saying it's east-west extension in these cases. You can choose a good one. Let's take that one and assume it's not quite so asymmetrical. That's showing the red in the middle means that you're extending the crest vertically, you're shortening horizontally. And the orientation of the shortening here would be northeast-southwest.
Okay.
In that case.
Thank you.
And then you go around, but these are a little more complicated. These are really showing that India is sliding underneath Himalaya at a general angle. Same style of faulting, but we interpret it slightly differently.
Sure.
If you know strain, think of these as lower hemisphere strain, lower hemisphere projection of the strain field. That's a way of looking at it.
Thanks for such a really interesting lecture. You're dealing with periods that are vastly longer and problems that are much more fundamental than the question that I'm about to raise, but maybe your research could shed some light on the likely effect on the whole monsoon system of the kind of global warming that we're beginning to experience now.
First, let me tell you the age. I gave a lecture, not on this, to my granddaughter's first grade class, and I said, now this is a long time ago, 100 million years ago, and you guys are 6 years old, and this one kid said, my uncle is 70, and he's still alive. You ask a good question, and it's unknown. I mean, people run models. Models for the monsoon are not very good, and we don't know. And my impression is that the models say that you should get more rainfall, but if you look at the past 30 years, the monsoon has been weakening. So there's something we don't understand that's going on, and I don't know what it is. You would expect, yeah, you warm the earth, you might get a stronger one. Actually, there's a reason you might not. If I can find just use, oh shoot, I went the wrong way. To get a strong monsoon, you want India to be hot, but you also have to draw this moisture in. And I have a colleague who thinks the real key is not so much how hot it is in here, but the contrast. So if you get India to be warm enough and it draws moisture in, then you increase the humidity, so you increase the moist static energy, and then up you go. If both are warm, you don't have that contrast, so you might suppress it. So there is a view that warming will actually suppress the monsoon. Whether that's right or not, I think we have to wait. And judging by the color of your hair, I suspect you and I might not witness. We don't have to worry about it yet. But it's a wide open question with arguments all the time and zillions of calculations, and you don't know what to do.
Have you looked at other areas of the Earth where analogous dynamics might prevail?
Yes, I feel the whole world is my domain. And aspects of this, the Andes, for instance, you don't have a collision, but you have a big, wide, high plateau. You're short crust, you're building high terrain there. We had this in Western North America. It's now, one can look at this as a history of first you build an Andean type situation, and maybe you start to have it fall apart, as in the Himalaya. Western United States has fallen apart a whole lot. If you had been in Nevada back 40 million years ago, chances are you would have been at 4,000 or 5,000 meters elevation. That's what we think. So we see this evolution now. Do we have anything like Tibet to study today? Yeah, we have Iran. This is kind of a miniature example, but it's much smaller. I would argue it's similar, but at an earlier stage. It hasn't started to collapse, hasn't started to fall apart, as Western United States has, as there's hints of this happening in the high Andes today. So I do think that we see the same processes, but we don't, we're always getting snapshots. The present day is a snapshot, and the snapshot here is what you would get at different times in the past in other places. But overall, yeah, the dynamics as I've laid it out is similar. The details, of course, well, we disagree on the details anyway, so we don't even know how different they might have been.
If the plateau is essentially irrelevant to the process, then might Antarctica present an example?
Well, geologically, Antarctica's history is completely different. It has a high mountain range, of course, the Transantarctic Mountains, but that's not built by these processes at all. I think you just have a hot upper mantle underneath. You have thermal expansion, so it sticks up high. It's a completely different process. West Antarctica is a little bit different, but still, it's not high. So I would say no. That's a very different environment from what I'm talking about here.
Peter, do you have a feeling for how high you expect eastern Tibet to be to make your story about a wet eastern Tibet and dry Pakistan work? And
I'll take anything. Whatever it takes, I'll be pleased. 25 years and no, I don't. I mean, that's the problem with Boosa's work is beautiful. It's just wonderful work, but he ran the code twice. One would have to run the code with do real experiments, not just 2 runs. So I think it hasn't been done.
And so also on that broad topography as opposed to a high Lungmen-Shan?
The Lungmen-Shan might do it. That might be enough. I just look at that as the edge of the high terrain. It does stand up a little higher, but maybe I should be careful. I haven't thought much about this.
I asked because of the colleagues who have recently published older ages for generating the topography along the Lungmen-Shan, if that would matter, as opposed to what the interior of eastern Tibet might have done.
And Marin's talking, the Lungmen-Shan is this mountain range right in here, which is very spectacular. You just look up, it's very abrupt topography. There have been arguments about when that topography formed, and recent studies are suggesting that it's older than 10 million years. I didn't find all that convincing, I have to say. But that's just a small part. I really think you need the whole thing. But you raise a good question. Maybe I'm just wrong again, and I should just give up. But I'm not going to. No way. Not what?
Not for at least 2 weeks.
Not for at least 2 weeks. Yeah, Nathan and I are gonna. God, we're gonna have a great time. We're gonna go out here in 2 weeks. Phone won't ring. Won't get email. Plus, it'll be beautiful. And there'll be no people except us. Just yaks and Anyway, I'm waffling here. Thank you. You're all free to leave if you didn't think so.